Hello everyone, today we are going to explore the structural intricacies of cluster compounds. Our discussion will focus on Wade's rule and the polyhedral skeletal electron pair theory, commonly known as PSEPT. These are the fundamental tools used by chemists to predict the geometry of complex molecular structures. Now, let's take a look at our roadmap for this session. We have structured this presentation to guide you through the theory in 4 logical steps. First, we will dive into the core concepts. Here, we will understand the mathematical foundation of Wade's rule. We will learn how to calculate the total valence electron and determine the skeleton electron pairs, which is the magic number needed to unlock the structures of any cluster. Once we have our numbers, we move to the structural classification system. This is where the theory gets visual. We will categorize molecules into specific structural types. Closure for closed case, Nido for nest-like shapes, and Direcno for web-like structures. These steps helps us see the relationship between electrons and geometry. In the third step, we will perform a comparative analysis. Instead of just looking at formulas, we will compare different boranes and carboranes side by side. This will help us understand why one molecule is more stable than another, and how removing a vertex changes the entire shapes of the cluster. Finally, we will wrap up with a conclusion. We will summarize the key takeaways, ensuring you have a solid grasp of how to apply PSEPT to any chemical problem. So, let's jump into our first topic, core concepts and formulas. First, let's define the theory. PSEPT or Polyhedral Skeletal Electron Pair Theory is a systematic framework. Its primary goal is to predict the 3D structures of cluster compounds, especially boranes and carboranes. The key takeaway here is that the theory creates a direct link between the number of skeleton electron pairs and the number of vertices in a molecular shapes. Moving to the core concept. Wade's rules are entirely grounded in electron counting. We start by finding the total valence electron. It's important to remember that in a cluster terminal, boron and hydrogen unit each contribute 2 electrons to the bonding. But it is the remaining skeletal framework electrons that actually define the final geometry. To put this into practice, we use these two simple formulas you see on the screen. First, we calculate skeletal electrons by taking the total valence electron and subtracting whole 2 into n, where n represents the number of vertex or boron atoms. Next, we find the skeletal electron pairs, dividing that number by 2. This SEP value is what tells us which structural category the molecule fits into. As you can see at the bottom of the slide, these calculations lead us to 3 main structural types. Closure, a completely closed cage-like structure. Nido, a nest-like structure where one vertex is missing. Arachno, a web-like structure where 2 vertices are missing. Now that we know the math, let's look at the actual shapes. Moving on the next slide. On the far right, we see the parent polyhedron. Think of this as our template or a starting point. It defines the maximum number of vertices that our cluster could potentially occupy. In this example, we have a template with 12 vertices. First, let's look at the closure structure. The mathematical relationship here is n plus 1 skeletal electron pairs. Geometrically, it is a complete cage with no vertex missing. Every corner of the polyhedron is occupied by an atom, making it the most compact structure. Next is Nido, which follows the n plus 2 pair relationship. You will notice the word Nido means nest-like. This is because we have one vertex missing from the parent shape, leaving behind a more open bowl-shaped structure. As we add another pair of electrons, we get the arachno structure, which follows the n plus 3 pair rule. Arachno refers to a web-like appearance. Here 2 vertices are missing, making the cluster look even more out and open. Finally, we have the hypocategory, following the n plus 4 pair relationship. In this case, 3 vertices are missing. While these are less common, they represent the most open nest-like geometry in this series. Now that we have our skeleton electron pair count, we can use the n plus x relationship to classify our cluster. Here, n represents the number of boron atoms in the parent polyhedron from which the cluster is derived. When our relationship is n plus 1, we have a closed cluster, as you can see in the first row of our table and the visual above. This is a complete closed polyhedral cage with no vertex missing. In the SEP count increased to n plus 2, the cluster is classified as nido. The term nido means nest-like because it is essentially a closed polyhedron with one vertex missing, creating a more open structure. Moving to an n plus 3 relationship, we get an arachno cluster. Arachno refers to its web-like appearance. Geometrically, this is a closed polyhedron with 2 vertices missing. Finally, n plus 4 relationship give as a hypocluster. This is an even more open cluster where 3 vertices are missing from the original closure form. Now that we have covered the general rules, let's apply them to real-world chemical specimens. We are going to look at the transition from a parent cage to nido and arachno forms. First, let's examine nido pentaborane 9. As you can see in the first column, this cluster is derived from a 6-vertex closed octahedron parent. By removing one vertex from that parent cage, we get the nest-like nido structure. If we look at the math, the skeletal electron pair calculations gives us 8 ACP. Since n is equal to 5, 5 plus 2 is equal to 7 pairs, confirming its classification as a nido cluster. Next, we have arachno tetraborane 10. This example is particularly interesting because it also derived from a 6-vertex closed octahedron parent. But this time, 2 vertices have been removed, following the vertex removal logic. Removing 2 corners result in the web-like arachno geometry. Our calculation shows 7 SCP with n is equal to 4 boron atoms. The relationship is n plus 3, perfectly matching the arachno definition. In our PSEPT examples gallery at the bottom, you can see the physical models. Specimen 1 shows the cage model for the pentaborane nest, while specimen 2 shows the frame model for the tetraborane web. These models clearly demonstrate how the loss of vertex driven by the electron count directly impact the 3D space the molecule occupies. This comparative analysis proves that the parent cage stays the same, but the number of electron pair detects how many vertices are actually occupied by atoms. Now, let's wrap up everything in our conclusion. The essence of this theory lies in the skeletal electron pairs as we have discussed. N plus 1 gives us the symmetry of a closed cage. N plus 2 opens it into a nido nest. N plus 3 creates the arachno web. And N plus 4 leads to the hypo network. Everything structural transition corresponds directly to the sequential removal of vertex from a parent closed polyhedral cage. Looking at our final specimens on the table, you can visualize this progression from the complete gold closure essence to the open silver arachno essence. The physical reality of these molecules is a direct result of their electronic signatures. Thank you for watching and thank you for being a part of this learning journey. Don't forget to like and subscribe for more deep dive into the world of chemistry. This is Alchemist for teaching and I will see you in the next one.